what we're starting with is our uh, equation that we derived in part A. So on our left side, we have our first derivative of temperature with respect to time, and then on our right side, we have our second derivative, temperature, with respect to our position. So this is how we are estimating our second derivative here, and this is our estimation of our first derivative of our temperature with respect to our time here. So the main thing that Crank-Nicholson changes with our estimation of this temperature change is it uses both this previous time step, or I guess the current, and it also uses an estimation of the next time step. However, we add them together and take the average. So what our initial Crank-Nicholson will look like is, well, the first thing we'll do is we'll move our change in time over again so we can get our R. And we have Tj n plus 1 minus our Tjn is equal to R times, and this is where things are going to change. So instead of having just our Tjn, we're going to start with our Tn plus 1 and j plus 1 minus 2Tn plus 1 j plus Tn plus 1 j minus 1. So we'll take this, and then to that we will add our Tj plus 1, well, not plus n, plus 1 of our current time, n, or current temperature, n, minus 2Tjn, then plus Tj minus 1n. And then lastly, we will take the average, add them together, and then divide them by 2. So we'll start like this. So as you can see, we have our Tjn over here and our Tjn plus 1 over here. What we can do with that is separate our terms to get our Tn plus 1s and our Tn's on the same side. So we can move this 2 out to be with this R. So we'll start with our R over 2. And then that's going to be multiplied to both of these. So we'll have just this down here, same thing, and then also plus our R over 2. And we will have this one here. So what we need to do now is we're going to bring our Tjn over and then subtract our Tjn plus 1s from the right side to the left. So what we should end up with is our Tjn plus 1, and then this is going to be subtracted over, so minus R over 2, and we have Tj plus 1 n plus 1 minus 2 Tj n plus 1 plus Tj minus 1 n plus 1. And then on our right side, we have R over 2, and then Tj plus 1 n minus 2 Tjn plus our Tj minus 1 n. And then this Tjn is moved across, so plus Tjn. Now we have our Tn plus 1s and our Tn's separated. So what we can do now is, because our R term is equal to, so currently our R is equal to our change in time times alpha, just our change in position squared. We can incorporate this 2 into it just to make things a little simpler. So from now on, our r is incorporating this 2 here. So this will just be r, this will just be r. And what we can do is multiply this r into all of these, giving us r times n plus 1 j plus 1, 2 times r tj n plus 1, and then r once again. We can do the same thing over here, r, r, r. So now we can get rid of these brackets, parentheses, and incorporate our tj n plus 1 and our tj n into these things. So on our left side, we end up with minus r times t j plus 1 n plus 1, because we have the negative out here, so that's negative. Then we have plus, we have 2r tjn, and we also have 1 tjn plus 1, so we have 1 plus 2r times tjn plus 1, and then we have just our r minus r tj minus 1 n plus 1. So that's our left side, and on the right we have r times tj plus 1 n. We have our minus 2r tjn and then plus tjn, so we'll end up with, go plus, we have 1 minus 2r tjn, and then lastly plus r times tj minus 1. And that is our algebraic solution to our first, or our time-dependent derivative of temperature using the Crank-Nicolson implicit differencing and then taking the average of the two. Okay. What we can do now is a stability analysis of our new algebraic equation to see at what point, if any, our r becomes unstable. So we can go back to what we used initially. So we know our tj plus 1 of n is equal to I k delta x times tjn, and our t n j minus 1 is equal to e negative I k delta x times our tjn. So we can substitute that into our new equation here. We have that here, so we end up with minus r times e to the I k delta x, and we have our tj of n plus 1 plus, we have our tj n plus 1 here already, but we'll multiply it out. So we have tj n plus 1 plus, again, 2. We'll put the r in front to make it easier to pull out later. R times 2 times tj n plus 1, then minus r times e to the negative I k delta x times tj of n plus 1. So we can do the same thing for the top up here, giving us, so we'll split these up, giving us r times t times e to the I k delta x of tjn. Then again, splitting these up, plus tjn minus r times 2 tjn, and lastly plus r times e to the negative I k delta x times tj n. And now what you can see here is we are able to pull out our tjn, leaving us with a slight interruption from the roommate. No worries. Okay, so what we need to do now is pull out our tjn plus 1s and our tjn's. So what we get is minus r e to the I k delta x plus, we're pulling out our tjn plus 1s, so we have plus 1 plus 2r, then we'll pull out our tjn plus 1, and then lastly minus r to the e negative I k delta x, and this is all multiplied by tj n plus 1. So what we can do here is we can move this 1 around to where we get 1 plus, and then we're going to pull out the r we have here. So we get r, and then we need to, wait 1 second, this is EIX plus, okay. So what we need to do is pull out a minus r here, giving us minus r. Then that will switch this sign around, so we will have EI delta x, EIK delta x, and then we will have again plus e to the negative ik delta x, and then lastly we'll have this 2r, which we pulled out the negative r, so we will have minus 2. What we know is that this is equal to 2 cosine k delta x minus 2. Now we have r, 1 minus r times that times tj n plus 1. So we'll do the same thing for this bottom equation right here, which is just our tjn's. So that will look something like this, as we'll pull out our tjn's, and we will have r e I k delta x plus 1 minus r times 2 plus r e negative I k delta x. This is all multiplied by our tjn. And then this time we don't need to pull out a minus r, so we will pull out positive r and move our 1. So we have 1 plus r e I k delta x plus e negative I k delta x, then minus 2, which is all multiplied by tjn. So now we have our two sides. I guess this needs to be turned to cosine, so we'd end up with 1 plus r times 2 cosine k delta x minus 2 times tjn. So we have this equal sign that we have kind of ignored until now, but these two sides are equal to each other. Now what we can do is pull out a negative 2 from both of these, giving us on this side 1 plus, because we pulled out a negative 2, 1 plus 2r times cosine of k delta x, which is now negative because we took out a minus 2, and then plus 1. times tj of n plus 1. We can do the same thing over here, pulling out a negative 2, giving us 1 minus 2r times cosine k delta x, which is now negative, plus 1. And this is all multiplied by tjn. So what we can do now is we can divide across by this left part and leave our tjn plus 1 on the left hand side, giving us tj at our next time is equal to our current tjn. Now we have 1 minus 2r, and we'll make this a big bracket here. We have 1 minus 2r, 1 minus 2r times 1 minus cosine k delta x. And then below that, we have 1 plus 2r, 1 minus cosine k delta x. So what we can see here is that we know for a fact that these two things will be true. That the value of our cosine cannot go beyond 1, meaning this number will always be beyond negative 1, or 1, meaning that this number right here will always be this part, 1 cosine k delta x is always going to be greater than or equal to 0. And we know that the value of r cannot be negative, so we know that r will also be greater than or equal to 0. So using this, we can combine this entire term to our 1 minus cosine k delta x into any variable, which we can call z. And we can see that there's two of them. So what we can now do is substitute this in, giving us tj n plus 1 at our next time is equal to our tj current times 1 minus z over 1 plus z. And if we know that both parts of our z here, r and 1 minus cosine are greater than 0, we know that z will always be greater than or equal to 0. So, knowing our z is always greater than 0, if we are subtracting a positive number from the top, which is 1, and then adding a positive number to the bottom, which is also 1, we know that our top will always be greater than our bottom. Top always greater than our bottom, meaning that for any value of r, our system will be stable. For the last part of homework 2, we're going to use our Crank-Nicholson differencing in order to again simulate our temperature diffusion and then show that any value of r is now stable, which we just proved using our stability analysis. So we'll go to Python. One important thing we have here is our from SciPy linear algebra solve banded. That's how we're going to solve our matrix equation and use matrix multiplication in order to make lots of calculations all at the same time. And in our situation, we're going to have our initial r equal to 2. We're going to have 100 different sections of our heat that can diffuse through, and then we're going to set our left and right temperatures to be constant, 50 and 80. So the first thing we need to do is make an array of our variables, which is going to be our minus r's and our 1 plus 2r. So right here, so we have our minus r, 1 plus 2r, minus r again, and then this is going to be used to solve our banded equation. So to start, we'll call it our top, middle, and bottom. top. This is going to be np.full. We want n, and then we also want this to be negative r. We'll have our middle, which is equal np.full. Call this n. Then we want it to be 1 plus 2 times r. And lastly, we'll call it our bottom, which is equal np full of n. And then we want this to be negative r again. So we call it top, middle, and bottom because in the diagonal banded matrix, we want our middle to be this n 100, 1 plus 2 r's, and then our top and bottom on top of that will be just negative r. And then another thing we need to do is to define our temperatures. So our temperature is just going to be equal to np full. We want n, and all of these are going to be initially at 20 degrees Celsius. So now what we can do is we can throw all these together. We will call this B for now. Our B, wait no, this is going to be our sparse matrix. So we'll just call this sparse A. This is going to be np dot r underscore. Then we want our top. Yeah, this needs to be, yeah, top. Then our middle. And lastly, our bottom. What did I do? Just need to be brackets. Okay. So then we can take a look at this to make sure it looks right. There's A. It should be 2D array with all of our negative r's, our 1 plus 2 r's, and then another group of negative r's. We now need to plot out what our diffusion will look like. So to do that, we'll need to make our subplots. So we'll call our figure, and we already have a figure up top, so we'll call it figure 2 is make underscore subplots, open bracket. And then we need to have a x-axis for this, and which is going to be our position. So all of our positions are equal to all of the ends we have in the middle, and then our left and right. So our position just be equal to np a range. Then we have our 100 in the middle, and then we need to add 2 for our t left and t right. And then we're going to repeat this for 2500 time steps. So for I in range 25 from 1 all the way to 2500, we're going to repeat our calculation. And then we need to have our B, which is going to be equal to our right hand side of our equation. So if we look at our thing, our A, so our sparse A, what we have here, our banded, so as you can see, this one in the middle would be our middle, and below is our below bottom, and then our top. So our negative r's are 1 plus 2 r's, and then we have all of our minus r's again. So this is going to be equal to our initial middle, so our 1 plus 2r multiplied by t is going to set up our initial B. Now that we've created our B, which is our right hand side, we need to update our temperatures for every time step. So our second temperature all the way up until our second to last temperature is going to be changed by adding R times T, and then this will be, we'll consider this adding it from our right side. So if we start with our first one, the one to the right would be 2, and then this will go all the way until the end. The next thing we'll do is our same B's, we need to account for what's on the left side of each position as well. So 1 until our second to last again, but this time we'll be adding what's on the left side of them. So this will be our very first one r times t. We want our very first t, colon, and then all the way up until our second to last one, which would be -2. Now that we've done all of our temperatures in the middle, we need to account for our ones on our ends, which are adjacent to our t left and our t right. So our first value in our set be 0. It's going to be plus equals, we need our second value, so t1 times r, and also plus r2 times r times our t left, which would be the constant temperature on our left side, which is adjacent to our very first n, or our position in between. And then we need to do something similar for our last one. So our b minus 1, very last one, is going to be plus equals again. This time we need to go our t, but this is our second to last one, times r, plus 2 times r times this time our t right, which would be the one adjacent to our second, or to our last value of our middle numbers. So now, I guess we can just make sure that there's no problems here. So what we need to do now is our solve banded function. So we'll call this our x. It's going to be equal to solve banded. And we need our 1, which is our shape of our thing. And then we need to have our, I believe, sparse A goes first. Sparse A, and then our right side. So it seems to have worked. So now what we can do is our fig dot add fig2 dot add underscore scatter. We want our x values to be our position. Our y values are going to be equal to what we just called x. And then our name for this is going to be an f string. And then we're just going to call this time. And then our time in this case will be I, so to denote which point we're at. And then one last thing we need to do is add in this. So we have just one for our initial. So add scatter, x is our position. Our y for this will be our, we need to create just one thing, which is our t left, then our t's, and then our t right. See if this does anything. And then we just need to see our figure. Fig 2. It's really thinking. Please. Oh, this might take a while because it is trying to plot all 1500. Oh boy. Okay, so after looking fairly carefully, there are a couple things that were wrong. So one thing I noticed was that I accidentally had a plus there instead of a minus, which does make a big difference. And cleaning this up, because this is more what we would expect, but there's still a few things. So this needs to be row concatenated, and then this isn't time I, this is just going to be our initial values. So that's starting to look a little better. And then it's also important that we have our row concatenation of our t left and t right. Our bottom part, t left, x this again is going to be a row concatenation. Getting a little closer. So as you can see, it's starting to change slightly. And then, oh, why is it still not wanting to work? This isn't minus. This has to be plus. Yeah, that's plus. Why don't you want to work? So, what's happening is I was trying to call this something different in order to not confuse myself with the two T's. However, that would be important that they are the same because it is stepping through time, meaning that it needs to be different or each one will be the exact same if it never gets updated. So that looks much better. So what we have here is now our initial time, t0 here. And now that we have changed this so that it updates our t instead of just redoes the same calculation 25 times or 2500 times, is now we have our temperatures at each time step. So as you can see, as time goes on, we get closer and closer to a steady state. And if we look at our very last time here that we took, it's nearly a straight line all the way from 50, our T left, up to 80 at our rightmost position. So one thing we can do now is try to prove that what we did in our stability analysis holds true. So if we increase our R, we can see that these bands begin to go to a steady state much, much faster. But as you can see, it doesn't go off into powers of 71 like before. However, if you do begin to increase it too high, you can see that there are some fluctuations. However, that because we proved this is stable, it will never continue to grow and will eventually become a steady state. Okay.